it's time to do some computation work to predict joint strength. We have two approaches, analytical methods or finite element method. In this module, we are going to discuss the analytical methods. It's time to discuss the methods that we have to design the joint. In any design, we need first to determine the stress level or the strain level in the structure and then apply a suitable failure criterion. That's what we are going to do. But we are going to do this first with the analytical methods. So methods that are relatively simple. We use concepts of mechanics of solids. At the end, we have one differential equation that has a direct mathematical solution. That's what we are going to see in this module. So let's start with the simplest analysis, which is represented in this slide, and assumes that the adherent does not deform at all. Only the adhesive deforms. And it deforms in a uniform way. So this is the undeformed state. If you apply load, then the adhesive will deform exactly the same way all along the overlap. And the shear stress formula in this case is simply the load divided by the resistant area, which is the width times the overlap. Extremely simple. This works very well, for example, for adhesives that are very, very flexible in relation to the substrate, like polyurethanes or like silicones, the elastomeric adhesive used in the aerospace industry. You just need this, you don't need anything else, all right? Now, the problem is that the adhesives that are used are not, for structural applications, are not that flexible, are not that elastic, are not that deformable. I'm thinking obviously about the epoxy adhesives that are quite rigid. We are talking about 3-4 gigapascal. This is sufficient to deform also the substrate. And this will cause a differential straining in the adhesive, which is represented here. The first to recognize this and to propose a model for this was Volkersen. So you have here the situation where there is no load applied, and here when you apply load. And of course the load, the transfer of load will be done like this from this side and will be done like this from this side. So this part of the substrate will deform much more than this one, and this will create a non-uniform deformation in the adhesive. The adhesive will be highly strained at the ends of the overlap and lightly strained in the middle of the overlap. And the corresponding stress or shear stress in the adhesive along the overlap is something like this. So you have a stress concentration at the ends of the overlap. So at the beginning, in the introduction, I told you that when you use adhesive bonding, you have a uniform stress distribution. That's true along the width. Along the overlap, it depends. If you have an elastic adhesive, completely true. If you have a rigid adhesive, not true. You have a stress concentration at the ends of the overlap. To illustrate the concept of differential straining, we have here a rubber model. For the substrates, we have hard rubber, and for the adhesive, a foam. At this stage, the joint is not loaded, so there is no deformation in the adhesive and no deformation in the adherent. But then, if we load the joint, clearly there are deformations, especially in the adhesive, but not everywhere. In the middle of the overlap, there is nearly no deformation in the adhesive, as you can see here. But at the edges, a lot of deformation. Okay, here and here. This is due to the load transfer in the adherents from here and from there. That leads to high deformation here and nearly no deformation there. And this difference in deformation of the adherents leads to high strains at the edges of the overlap in the adhesive. Very good. But Volkersen ignored an effect that occurs in the single lap joint, and that is quite important, which is peel loading. And why do you have peel loading? Because the load is not aligned. When you apply a load, you have a bending moment, in fact, because of the fact that the load is not perfectly aligned, which is the load times half the thickness of the substrate. So during the loading of the joint tends to align, and you have effectively a bending moment applied at the ends of the overlap, which causes peel at the ends of the overlap. Here in the adhesive, at the ends of the overlap, you have peel. And the corresponding peel stress distribution along the overlap in the adhesive is something like this. So again, everything happens at the ends of the overlap. So what Goland and Reissner did is they proposed an equation for the shear stress very similar to that of Volkersen, and in addition to that, they proposed an equation for the peel stress in the adhesive along the overlap. So a step further, let's say. Later, Hart-Smith proposed another model, which was a big step forward because it took into account the plasticity of the adhesive. Volkersen and Goland and Reissner, they just considered the elastic behavior of the adhesive. If you represent the shear stress, shear strain curve of the adhesive, you have something like this. It's elastic and it breaks. It doesn't have plasticity. And the first to take that into account was Hart-Smith. So this is the real shear stress, shear strain curve of the adhesive, and this is the ideal shear stress, shear strain curve that he proposed. Elastic, perfectly plastic. Now let's look at the stress and strain distribution for this case when you have plasticity in the adhesive. Let's look at point A, point B, and this point where the adhesive fails. Point A, basically there is nothing new in relation to Goland and Reissner and Volkersen. You are in the elastic part. So you have here for the strain, you are here for the strain, and you are here for the stress. There is nothing new here. Now, if you analyze the situation in point B, there is something new because now there is this plasticity in the adhesive. If you look at the strain, though, there is nothing new. It keeps straining because there is no limit in terms of strain. The limit is in terms of stress. And if you look at the stress, in fact, when you reach the yielding strength of the adhesive, then it starts to yield, and this part here of the joint has yielded, which corresponds more or less to this part here at the ends of the overlap. But it's not over because the adhesive can take more. The joint can take more because the adhesive can deform plastically. So it can take more. You go this way, the plasticity goes this way, it goes this way. And if you look at point C, which is when the adhesive fails, you are here and here. So the plasticity has progressed a bit further inside the joint until you reach the failure strain of the adhesive, and then the joint fails completely. But you still have here an elastic reserve in the adhesive. Imagine that the adhesive was much more ductile, then you could further plastify the adhesive inside the joint and use this part that in fact is not being used when it's elastic. When you look at Goland and Reissner or Volkersen, only the ends of the overlap work. If you use the Hart-Smith model, the whole or more overlap work, and the more ductile is the adhesive, the more overlap works. Ideally, you want the case where you have plasticity along the whole overlap. You have global yielding of the adhesive. That's the ideal situation. But this is really important because the plasticity of the adhesive causes a stress redistribution, and you are using the less stressed part of the joint that were not used previously if you use the model of Volkersen and Goland and Reissner. Okay, so I have a few models now that can give me the stress and the strain in the joint. I can apply now a suitable failure criterion. Which one should I apply? But it depends where it fails. Imagine it fails here in the adhesive, then we can use Goland and Reissner or Volkersen. Imagine it fails here, well, you can use nothing. This is forbidden. It cannot fail at the interface because there is not any failure criterion that can design the joint for you. Or it can fail in the adherent. There are also ways to design the joint when it fails in the adherent. Let's analyze. And let's start with the adhesive. So imagine it fails in the adhesive. Imagine it's a very brittle adhesive like this. Well, you can use either Volkersen or Goland and Reissner, easy. Now imagine that the adhesive is a bit ductile, okay, a bit ductility. You can use Hart-Smith. It fails when you reach the failure strain of the adhesive at the ends of the overlap. Now imagine it's very, very ductile. In that case, the whole overlap yields and you have global yielding. And you don't need any fancy equation. It's very, very simple in that case to design the joint, which is represented here. So on the left, you have the case where the adhesive has a limited ductility and only part of the adhesive will yield. And it will fail when at the ends of the overlap you reach the failure strain of the adhesive. Now imagine the adhesive is very, very, very ductile and you have plasticity all the way through until you have complete yielding. Then in that case, the failure load is simply the yielding stress of the adhesive times the resistant area, the overlap times the width. And again, this is something you can do by hand. You don't need any fancy model. It's called global yielding in the adhesive. It's nice to see in a graph load versus displacement that you obtain when you load a single up joint. What happens when you load a single up joint? Well, if you have just an elastic adhesive, something like this, it will fail somewhere here. If you have an adhesive that yields, you can go further and have a higher failure load. That's what does the ductility to the joint. It gives a much higher joint strength to the joint. Okay, now imagine it fails in the adherent. Let's start with low strength metals like mild steel or aluminum. Then you might have yielding of the substrates like this. Where is the place in the adherent where you have highest stress? It's the ends of the overlap, and this might be sufficient to cause plasticity, yielding of the substrate. And once you have yielding, then the deformation will be concentrated here, and if you have a good bond, a good adhesion between the substrate and the adhesive, then the substrate will pull locally the adhesive until it fails. In fact, in this case, what controls the failure is not the adhesive, it's the yielding of the metal. And if you want to have a good estimate of the failure load, you simply have to calculate the load corresponding to the initial yielding of the metal. All right? Here in this graph, you have the yielding of the metal. In this case, it's where you don't have the yielding of the metal and the adhesive, if it's ductile, can work in peace. But how do you calculate the load corresponding to initial yielding of the metal? Well, it's very, very simple. You have the tensile component and you have the bending component. So tensile and bending, you add the two and then you calculate the load for the case where you have yielding of the adherent. There is a factor K that appears that is related to the Goland and Reissner factor that was calculated previously. But you can simplify the expression and you can say that this value K is equal to 1 when you have low loads and short overlaps, or 0 when you have a long joint when compared to the adhesive thickness. The two cases are represented in this graph, load versus overlap. So this equation, when K equal 1, you are here, and when K equals 0 from that point, when you have a long adherent compared to its thickness, you are here. And in between, you can interpolate. So this is your limit corresponding to the initial yielding of the metal. The other limit is the global yielding of the adhesive. Imagine you have a metal and a very, very ductile adhesive. You are here. Imagine you have a very, very ductile adhesive but a low strength metal. You are here. Okay? Understanding the joint mechanics is nice to understand or is useful to understand the effect of disbonds. Places in the adhesive joint where you don't have adhesive that can occur typically in the middle, because the edges with your eyes you can see if there is adhesive or not. But in the middle, is there adhesive? If you understand this, that I explained, and the global yielding of the adhesive, then you can understand what's the effect of a disbond in the joint strength. Let's look at this graph. You have failure load versus defective area. This is the defective area. Here you don't have any defective area, but imagine you have a high strength steel and very, very ductile adhesive. Then the failure is dictated by the global yielding of the adhesive. And see if you have a defective part in the middle, the more or the bigger is the defective part, the lower will be the joint strength. It's proportional. Now imagine you have a low strength steel or aluminum. Everything takes part here, and doesn't matter what you have in the middle. What the joint strength is controlled by what happens at the ends of the overlap. That's why big or small defective area doesn't matter. It gives exactly the same failure load. Now, on the other hand, imagine you have a very brittle adhesive, something like that we saw with Volkersen, Goland and Reissner. And you remember that the joint or the stress distribution is something like this. The middle is doing nothing. In this case, it doesn't matter if you have a strong adherent or a low strength adherent. Everything takes place at the ends of the overlap, and the size of the defective part doesn't matter at all. So you see the importance of having a disbond in the middle. Really, many cases doesn't really matter. If you use brittle adhesives, if you don't have adhesive in the middle, doesn't matter. It takes place at the ends of the overlap. If you use metals that yield, doesn't matter. It takes place at the ends of the overlap. When does it matter? When you have a very ductile adhesive and very strong metal, then it matters to have a defective part in the middle. Concerning composites, composites are very much used in airplanes, more and more. Fantastic materials in the direction of the fibers. You have very strong material. The problem is transverse to the material, in the thickness direction. Then you have a problem. You might have delamination of the material, as explained here in this series of schemes. So let's look at the loaded case here. This loading, as you know, introduces peel in the adhesive, but not only in the adhesive, also in the substrate. And because we have a very limited strength through the thickness in the composite, this might be enough to cause delamination. And it does not give the chance to the adhesive to develop its full capacity. It will fail prematurely because of the low strength of the composite. So when you use composite, be very careful with this aspect, with the low strength of the composite. So we have seen many things. We have seen many analytical models, many failure criteria. Maybe it's a bit confusing at the moment. Which one shall I use for a particular situation? That's why we decided to make a software that is very user-friendly and that will tell you which model is more appropriate for a particular situation in terms of geometry and in terms of material properties. This software.
Here we are going to start with a demonstration of our Joint Designer software. This is an online software that allows us to predict the strength of bonded joints using analytical models. Let's start with a new analysis. We're going to consider the single abstract geometry, and we are then faced with a menu that asks us about the material behavior. We're going to say that our joint has adherence with an elastic behavior and an adhesive with also an elastic behavior to keep things simple. Then we also define an isotropic behavior, so there is no directionality of the properties of the materials. Then we are asked for a load intensity. We're going to start with 1000 newtons, and this will create the stress distribution that will result from this target load. Module number 3 is the material properties model. Here we are going to select materials. So for the adherents, we are going to consider steel, which is already pre-selected here in this list. And then for the adhesive, we're going to consider, for example, RLD 2015, a common epoxy adhesive. Module number 4 will take us to the selection of the geometry of the joint. And so we're going to consider a joint with 2 millimeters of thickness in the substrates, with an adhesive layer thickness of 0.2 millimeters, and an overlap length of 25 millimeters by a width of 25 millimeters. In module number 5, we see a selection of possible analytical methods to solve this problem. This selection is a function of these characteristics here in module 1, because these models that you see here are also models that account for these characteristics that we see here, elastic behavior and isotropic behavior. I'm going to select one of the most classical ones, which is the Volkersen model. Then According to the selection of this model, we are asked for a failure criterion. This failure criterion will be the maximum shear stress. And if we know that our adhesive has a maximum shear strength of 14 MPa, we can introduce here this given load. We click compute and we get a stress distribution along the overlap line, and we get a limit line which corresponds to this failure criterion of 40 MPa of stress in shear. The only thing that we need to do is go here to the right side and now change gradually the load that we are applying to the joint. So for example, 3000 will generate 8.32 megapascal, 4000 a bit more, and let's go all the way up to 6000, and now we have passed our limit. So we know that it should be something around 5000, probably 5050, something like this. Okay, and so with this we have calculated, using the Volkersen method, the load that this joint will support before the stress in the adhesive layer reaches the maximum that the adhesive can sustain.